Good morning, ladies and gentlemen. The topic which I am going to talk on is UAV payloads for persistent surveillance. Just a moment. So this is how I would like to cover my topic. Brief introduction to persistent surveillance and the payload integration on UAVs. Key takeaways before I conclude. We all are aware of the threats which our country faces, and we have a wide variety of eminent people here. I don't have to go on speaking about this, but the idea is that we have a lot of security threats, especially land border threats, maritime threats, and threats from the airspace and internal security threats, which we have to cater for. So it is very important for us to have persistent surveillance, that is the ability to continuously observe an area over long duration and to detect, classify and track and predict all the activities which are going on. In this case, it is not just observation, it is having a continuous situational awareness of our surroundings. So this is a very critical thing which we have to have in our inventory. So we have to have surveillance regardless of time, terrain, weather and the threat environment. So what are the assets which are required for persistent surveillance? We have different type of UAVs. We have a lot of people from the industry. We have experts who have operated the platforms. So we know there are various type of platforms which are currently available. We have nano UAVs, tactical UAVs, male, hail class of UAVs, rotary and swarm. So wide variety of platforms are there depending on the type of application which we are looking at. And we also have them operating at different layers. So we have the platform in place and we have the payloads in place. We have payloads for surveillance in different parts of the electromagnetic spectrum, that is in the electro-optic, IR, SAR, ELINT, COMET, LiDAR for 3D terrain mapping. So we have a wide variety of applications and wide variety of payloads to cater for that applications, and we also have the platform. Now the issue is additional platforms we also have on EW, like in case of jamming or spoofing or carrying out electronic attack and communication relays. So battlefield communication and data relays, they are very critical when there are operations in place. So we have to have a synergy between the platform and the payload, which is very important. We're not going to details of the payloads because payloads are specific to the requirement and the part of the electromagnetic spectrum, but we also have to have a complete matching of the payload with the platform. So there is a very high requirement of having sensor fusion. The data from the payload is a raw data which actually has to be processed. However, after processing this data, since there are a multitude of sensors which are available right now, it is also that the sensors are also observing a single target or same target. So we need to have AI which combines all the information which is coming out and only sorts out the intelligence to transmit this data to the commanders who are the decision makers. Because unless we do it, we will be unnecessarily using the bandwidth which is going to saturate the bandwidth, which is to be avoided. So sensor fusion is one aspect which we should look into, and it improves the detection probability, tracking and the target classification accuracy. We also have to have something called a layered UAV architecture, wherein we have UAVs of different types operating at different layers, carrying a very specific payload, so that the complete picture, the situational picture which is required by the commanders will be available on a single glass pane. So we have to have the commanders having a complete view, not trying to think about the sensor which is giving or from which UAV it is coming. So all these things have to be fused together. It has to be a layered information which is presented to the commanders. So I am from the Directorate of Aerospace Design, and we are in constant interaction with the Indian industry, private industry, to get them into defense production and manufacture design. And we have a lot of projects which are ongoing. A few of them are shown here. We have drone-based EW system, collaborative swarms, airdrop canisterized swarms, then unmanned CSR, airship-based HAPS, fixed wing. We have a lot of projects under MAKE and IDEX and TDF. And in this, we give a problem statement to the industry, the problem which the users face or some problem which we need a solution for. We put it up to the industry, and the industry comes up with a solution. Most of the time we don't even specify the type of platform which we want. It is left to the industry to come up with a solution to solve this particular problem. And we have very good capability in the industry who have come up with some very good solutions, and these projects are at different stages. Some are in the UI stage, some have already reached the stage of trials, SSCT or FET trials, and we have some which we have given AIP, and there are some which are still in the pipeline which are going to come up. So we are progressing in a way where we have a lot of inputs from the industry and a lot of support from the industry in these particular cases. So these are the few of the projects which are UAV related under MAKE. And similarly, we have project under IDEX. This is for small SMEs and individual innovators and small companies, where similar projects have been given. Helicopter launch swarms, multi-role autonomous UAVs for air defense. There are a lot of other projects, and the payloads are also a wide variety of payloads we are using. And we also have the platform which the industry decides how to actually execute this particular problem. I mean, how to find a solution to this problem. So now I would like to cover the focus areas for the industry, because we have a lot of industry reps here, and I would like to cover the areas in which they should be focusing. The main thing which I feel is we have the payload, we have the expertise in the payload, we have the platform. We also have to look at integration of the payload with the UAV. So integrating payload into UAV is actually a system engineering problem. It is not simply a mechanical mounting. We can't consider the UAV as a platform, just a platform to mount different type of payloads. We should integrate the payload with the platform seamlessly. And there is a tightly coupled interaction between the payload, the aircraft, the data link, the power system, mission computers, RF environment, autonomy, and operator workflow. So there has to be a complete matching between the payload and the platform. So when we compare the integration of the payload with the manned and the unmanned aircraft, because we have enough expertise in integrating payloads to manned aircraft. We have an agency with an organization called AST, where we do all the integration of payloads and systems on the aircraft. So we have sufficient experience in that. But UAV is a different game altogether, where we have certain, you can say, differences between these two integrations. We have human in the loop in case of manned aircraft, where we can compensate for some problems or some thing which has come up which is not planned. However, in case of a UAV, everything has to be programmed. We have to learn everything. We have to program the system so that if there is any failure, the system is already knowing what to do. So it cannot take a decision which it is not trained, or in which it is not programmed. Another problem is the power availability. Usually in a large aircraft, we have systems with environmental cooling systems. We have generators which can actually power the payloads. Whereas in case of a UAV, the same payload, the same power source which is powering the engines, the motors, has to actually give power to the payload also. And cooling is a big issue because of thermal hotspots which are created, vibration in case of propellers, and in case of UAVs it is quite a severe problem. And size, weight, and payload constraints are a big issue in case of UAVs. And placement of antenna, because of the restricted space, it is very difficult to find a place for optimally placing the antennas in a UAV. And we also have issues of maintenance, flight endurance impact. Safety certification is one of the most important things, because we have evolved a system of safety certification in case of manned aircraft, whereas in case of unmanned aircraft, we are still evolving this certification process. We have some in place, but still it needs to be evolved with the different type of systems which are coming up so quickly. And also EW survivability, EMI, EMC, redundancy, and also since there are a lot of RF emitters on the UAV, we have to cater for all the EMI, EMC issues, which is very, very stringent in case of UAVs. So we need to understand that in case of a manned aircraft, the aircraft carries the payload, whereas in an UAV, the payload and UAV become one tightly coupled cyber-physical system. So we can't isolate both of them. We have to integrate them as a single system. So we have certain domains where we need to look into when we are integrating the UAV payload, payload onto a UAV. the mechanical integration, the aerodynamic integration, electrical power, EMI, EMC, because the system has to work without any problem. It should not have, because the same payload which is working perfectly fine in a manned aircraft may not work the same way in a UAV. It is different because there are other problems which are associated with it. So we have to look at it in a different way when we are actually doing it. And also the data network integration, which is very important because the communication is very, very important. Data link is very important when we are talking about UAVs. And mission system integration is also very important. Certification, which I have already said, is again something which we should look at. And we have certain failures which we have commonly seen when we do our SSCT, when we do our trials. We also find that there are many industries where they fail because they have not catered for certain faults which may come up. It is like it's different from what we do when we do manned aircraft integration. We have problems there, but here the problems are different. So we have to cater for these problems like RF self-interference, grounding, CG shift, vibration. These are some of the problems which we should actually address. And payload integration, there should be a complete roadmap. The roadmap has to include right from the beginning with the mission in view. The mission has to be thought out, and after that the payload integration has to be a part of that. And then there should be a swap budgeting very early, and selecting the right UAV platform for a particular mission is very critical. So once we understand which platform is going to be suitable, we can't swap just the platform, the payload onto a platform which is available with us. We need to choose the platform correctly for the particular mission. Navigation, architecture and our systems which are there. Test and validation, again, is a very, very important aspect of integration of payloads onto the UAVs. Initial lab testing is where we should actually take out all the problems related to EMI, EMC, electrical interferences, and software bugs if there are any. So the lab testing has to be very stringent, and it has to have all the test cases where possibility of failure is there. And coming to the ground integration, the integration of the payload on the UAV, different type of payloads, where are they going to be located? Because the same payload, the payload may have to look at the same place. The different payloads may have to occupy the same place. The EU and IR cannot be located at different places, because if you want to stitch them together, they have to be located at the same place. So it is having a different, the constraint of space. Taxi hover testing, which will give us details of any problems which will come up, vibration and things like that. Incremental flight testing and operational stress testing is where we will understand the complete operational philosophy, if there is any limits in terms of in the environment in which it is going to operate finally. So there are key takeaways which I would like to emphasize on. This is especially for the industry and for others who are also here, that persistent surveillance is no longer an option. We have to have complete situational awareness. Like Air Marshal Dikshit said, our eyes should always be open. We can't even close it for a short time, because we will lose that situational awareness for that particular time. UAVs are central for future ISR architecture. So whenever we have different platforms, whether manned platforms for ISR, we have satellites which are carrying ISR payloads for persistent surveillance, but UAVs are going to be a very, very important part of this architecture, and they have to be fused into that architecture, like connecting them through AI and sensor fusion onto the ISCCS network, and the entire situation should be available to the commanders at one place without having to worry about where this data is coming from. Sensor fusion, like I said, is very important rather than taking data from the individual sensor capabilities. AI-driven analytics will determine the operational effectiveness, because we have AI models which are doing a very good job, and then we need to use this particular technology to give us more intelligence rather than information when we try to integrate these payloads onto UAVs. And also counter UAV capability, it is very important.
So you'll have about 2 minutes left.
Technologically, we know that all the payloads complement each other. We cannot have these payloads in isolation. We have to have these payloads fused together. Like I said, multi-layered and multi-UAV architecture provides us reliance and standby. Indigenous development, like it has been mentioned earlier, is very important. We should focus on that. Manned and unmanned teaming, which has already been told, it is going to be the operational standard shortly. And industry, we are it is mandatory that we have academia, industry and defense collaborating together. This is very critical because many areas there is research going on, papers are being published, but nothing is coming out as a product which we have to focus on. Modular open architecture is very important because with that we can interchange the payloads very easily. We can upgrade the software of the payload. We are not dependent on one single vendor to upgrade our systems. So this has to be something which the industry has to work out and give it to the forces. Indigenous payload ecosystem has to be prioritized. And in conclusion, I would say the future conflict will be won not only by firepower, but also by information superiority. So this is one thing which we should understand here. Persistent surveillance through integrated UAV ecosystem provides us early warning, decision superiority, operational dominance and strategic deterrence, which will help us take a good and effective operational decision. And we must also build a resilient, indigenous and AI-enabled ISR architecture, which is very important for us to focus on. And with such a important and eminent audience here, I'm very sure that a lot of ideas will come up, and we will have a very good ecosystem, and we are working towards it. And I thank each and everyone for this patient hearing, and thank the chair for giving me an opportunity. Thank you so much. Jai Hind.